Hello and welcome back to the Everything EOS podcast. I'm your host, Brandon Lovejoy, and my co-host today is ENF developer advocate Jonaed Iqbal. Jonaed, how are you doing today?
I'm doing well. I'm really excited to go deep on a topic that I know very little about, so I'm glad that we're surrounded by experts who are working on these things who can answer our questions.
Absolutely, me too. Yeah, it's going to be a real deep dive. We're going to get into a very prolonged technical discussion with some remarkable engineers that we're fortunate to have with us here today. We have Areg Hayrapetian, Director of Engineering with the EOS Network Foundation, Guillaume Babin-Tremblay, which my French will not allow me to pronounce correctly, Lead Developer of the UX Network, and Matt Witherspoon, Principal Engineer with the EOS Network Foundation. Glad to have you guys all with us today.
Thanks for having us.
So we have an extraordinary amount of ground to cover. Why don't you kick it off for us, Jonaed?
Yeah, I'm really excited to talk about this topic. So there's something called IBC. What is it and why do we even care about it?
Sure. Okay. So I guess IBC stands for inter-blockchain communication. There's a number of different, implementations of this technology, and they might mean slightly different things depending on the concept. So here, as it pertains to us in the Antelope ecosystem, we refer to the Antelope IBC as essentially like this ability for a smart contract on a given chain to prove that a certain action took place on another blockchain in a way that is consistent with the consensus rules of that other blockchain. So at the core, this is what we mean by IBC, and it's a foundational block, I guess, on top of which several other applications can be built.
Yeah, so I think some of those applications that people are most familiar with is just moving tokens around. I think that's like the most primitive form of IBC that people think about. And when we're talking about IBC, we're talking about something a lot more foundational and general than that. We're talking about just the ability for two contracts or two pieces of software to communicate even though they live on different blockchains. One application being you lock up a token on one blockchain and then send a message to the other one to say mint some of this wrapped token here so it's accessible on the other blockchain. But you could imagine doing more sophisticated things like sharding your application across two different blockchains as a means of scaling out the application, for example. Or so many other possibilities as well.
Cool. Matt, anything to add to that, or that
I don't. I think that's well covered. Yeah.
Cool.
So now the next topic, instant finality. What is that and why do we care?
I guess I'll let you start with that one, Areg.
Okay, sure. I'll start with finality. So finality in the Antelope space, I think we tend to use irreversibility instead, but finality is a more common term in the wider blockchain cryptocurrency ecosystem. This idea that so as blocks are being added to the blockchain, initially the block is just really a proposal and it's not yet final. It's not irreversible, meaning it could be forked out and replaced by some other block instead. Finality is when you can actually trust that the block will remain. It won't be replaced by something else. And so the side effects of that block you can count on. So for example, if you receive some cryptocurrency in exchange for some trade or something, you want to know that your money is going to remain there. It's not going to disappear suddenly. And so it's important to ensure that the transaction is final, which means the block that the transaction was included in is final. And an important metric when we talk about finality is time to finality. So basically, how long do you typically wait from when you send the transaction to when the transaction is included in the block and the block is final? Because that that's finality is what you care about. Ultimately, that latency is what's really important. So for Antelope as it exists today, the algorithm that we use is such that it depends on the number of block producers. So on EOS, for example, there's 21 block producers. It depends on that number for how long you have to wait, how many blocks you have to wait, and therefore how long you have to wait to reach finality. And so on EOS with 21 block producers, it takes 3 minutes. If you were to double that, it would take 6 minutes. So instant finality is a new consensus algorithm for finality that fixes that issue, and it does two things. One, it makes the time you take very weakly dependent on the number of block producers. Basically, it's more or less irrelevant. And two, it just reduces that number way down from 3 minutes to basically low single digit seconds. It depends on how distributed the network is, but it basically starts becoming low enough that it depends on how quickly messages can be sent across the internet. Guillaume, if you...
Yeah, no, I think it's a great explanation of what these things, like what finality, reversibility means. And I guess the reason why it matters to reach that finality faster is whenever there is a service or product to be rendered in exchange, say, for a payment, there's always a window of time where that transaction could be reversed or could be, like forked out and would have to be retried again. So that introduces additional risks, like to the transaction, whatever the transaction may be. There's a window of time during which something can happen. Doesn't happen necessarily very often, but it could, and that could have consequences. So earlier we're discussing the concept of IBC. This is personally what led me to these questions about instant finality. When you're doing IBC, for instance, if you're going to be locking tokens on a given chain and minting other tokens on another chain through this protocol, now there is you have to ensure that the state on these two chains remains consistent in an atomic matter. So if you have a long time to finality, then you have to wait longer, or you risk having inconsistencies, and that of course impacts the user experience, slows down the workflow, and potentially makes some use cases not as attractive, essentially. So this, by achieving this faster finality, this instant finality, really, we're able to drastically improve the, user experience, as well as extend on the range of applications that are possible using IBC technologies, for example.
Cool.
Yeah. So, what makes all of you excited to work on this stuff? Because this is like a big milestone. I know scalability is always something about blockchain, right? To make it be used as something every day, as opposed to a fringe technology.
Well, go ahead.
Go ahead.
Okay. So I mean, personally, and talking more about, philosophy, or about my vision for these platforms. I mean, we can imagine. I think everyone who's passionate about that space can imagine a drastically different world in which a lot of, transactions, whether they're financial or identity related, or related to property, or related to contracts, or to any sort of, public transparency exercise in governance, and so on and so forth. I think there's a potential to be impacted by blockchain technologies and smart contracts. However, in order for this to happen, these systems have to be built with very solid foundational blocks, and with tremendous capability in terms of scale, in terms of throughput, in terms of load, and security. And there's the way to make it scale in many, many ways has to do with the ability of these chains to communicate with each other and to essentially allow for whatever innovation, whatever different governance mechanism to be applied to different contexts or to be experimented with, but still having I guess, like a common interface, a common way to exchange information and to distribute applications across these systems. So for me, like these two things are like IBC and Instant Finality. Both of them are critical building blocks in that I guess like system that I see at scale in the space. And these are also very cutting edge, I guess, like topics of research and development. So this is what personally gets me excited about these things.
What about you, Areg?
So when it comes to instant finality, first, there's two things, I guess, that I want to talk about there. So one is just in terms of enabling many different types of applications, perhaps a few minutes to wait for finality is okay for certain applications. It's a lot faster than maybe what someone might expect for settlement of some financial transaction. But when you want to expand the scope of what blockchain could do, the UX experience of waiting for that irreversibility can basically make certain applications just not really feasible in a friendly way. So bringing down the time to finality down to a very short amount of time, where we could almost say it's instant. I mean, it's not instant, but it's as close to instant as I think you're going to get in this global decentralized network. And it's actually quite fast. You enable other possibilities. So I'm thinking, for example, games. Games I think is probably a good application. Obviously, not fast enough for certain types of communication on games where you're talking about milliseconds, but once you get it down to seconds, like there's maybe sort of turn-based games or something like that, where that's fast enough that it's no longer a barrier to using the blockchain, for example, to do that with instant finality. So that's one aspect of it that excites me. The other aspect is very behind the scenes that people, it was not visible to the user, but I care about it a lot, which is with this instant finality work, as part of the RFP, we've created requirements to ensure it has certain properties, and also to have, as part of the deliverable, proofs, mathematical proofs that it meets those, it achieves those properties, which I think is very important when we're talking about a consensus algorithm. And Antelope in its past has its current consensus algorithm that achieves certain properties, but it doesn't have that rigor that I would like to see. So we're kind of stepping it up and ensuring we meet that mathematical rigor that one would expect from something as fundamental as a consensus algorithm. For IBC, it's really about scale. It's not only about scale, so I guess two things there too. Scale is a multifaceted thing. It's not just IBC. I think there's lots of ways we can approach it to try to horizontally scale, both in terms of storage costs and in terms of just throughput, transactions per second. But certainly, I think IBC is a critical component of that. One of the significant options we need to consider for how we horizontally scale and achieve much larger numbers for aggregate throughput that a lot of people would like to see and maybe have heard in the past. IBC has been talked about in the EOS space for a long while now, and we're finally actually seeing it come, to fruition soon. So that's really exciting. I think it's just the beginning stages. Like, this is just the building blocks of simple message passing. I think there's so much more that needs to be built on top of it to make it easier for an application to actually leverage a multi-blockchain platform and scale that way. But already a lot can be enabled with what's coming with IBC as part of this initial deliverable. The other aspect as well is, even beyond scale, it's not going to be a single blockchain rules them all environment, right? There'll be blockchains that specialize in different niches, and there'll be different governance experiments. And I think it's important to be able to have these communicate together and kind of act as one whole cohesive ecosystem. So IBC enables that to beyond just scale.
Yeah, there is something there that, to continue on a little bit of part of your thought there, are really excites me specifically about the IBC aspect of Antelope, is that when the protocol was designed like 5 years ago, like the protocol was designed with this idea that you could do light validation of it to the smallness of like doing it inside of an Antelope contract. And I think it's really exciting to see those technical design decisions that were made many years ago pay off now, and it works like we expected it to. And it's great to see. It makes me excited to see what's able to be done with it.
Yeah, maybe just if you don't mind, I'd like to add a quick note there. As I started working on IBC, at some point, like I wanted it, I needed it, so I was like, okay, like let's work on that, let's get it done. That was very obvious that the design of Antelope, like ESIO at the time, Antelope now, had been carefully thought through and engineered in a way that would allow this. And kudos to you guys and to the rest of the team that worked on that originally, because it made everything a lot easier. Like, we've been doing the same exercise with other blockchains, with Ethereum, with Binance Smart Chain and others. They didn't take these kind of decisions early on, and that makes it a lot harder, a lot more difficult to build like a good IBC layer on top of it. So that's something that needs to be highlighted. I think you guys did a really good job in that original design, building on the shoulders of giants.
Sweet. Always good to hear. I'd love to get into what those design decisions are, but I think that's like a whole, maybe other conversation.
Yeah.
All right. Well, let's dive into IBC from, in the big picture view. This has been called Trustless IBC. Why are we calling it that? What makes it trustless exactly? Guillaume, to you first.
Yeah, I mean, I guess the term trustless, the way I look at it, is it does not require trusting any additional entities that you don't already trust in the process. So it's essentially, you're using a blockchain. Of course, if there's a consensus mechanism on that blockchain, in the case of Antelope like systems, you have a point at which the consensus rules are able to tell anyone who's watching that the specific block is final or is irreversible. So this consensus mechanism now has to be replicated in this IBC implementation to be quote quote trustless, to essentially achieve the same consensus guarantees that I guess are present in the original system. So this is what we mean. Now, there is, of course, when you are maintaining let's say a relationship about state on two different chains. For example, in the case of the wrap token, like set of contracts where you're locking, let's say, EOS on the EOS chain, and then you're minting them as a wrap version on, say, Wax. Now there is a like locked state between these two chains where essentially like there should be a 1-to-1 equivalency between the amounts of tokens that have been locked on EOS versus the amounts of tokens that have been minted on Wax. So as this, let's call it like a dual state, exists, you need to trust the governance mechanism of both chains simultaneously, because now there's a potential divergence in that state that could depend on like the governance rules or the processes or system contracts or other contracts, the token contract itself, that could potentially affect this joint state. So it's the way I like to define it is it does not require additional trust in entities that are already trusted implicitly by performing that action.
Sweet. And I've talked to Areg a little bit about this. Curious what you have to add about the whole trustless question.
Yeah, I mean, I basically just kind of agree with what Guillaume says, that that's the way I would look at this word trustless. I've had some objections to the word trustless, mostly pedantic, but I think it's worth, there's some that is worth pointing out, as Guillaume already has, I won't restate it, is that there's always something you trust. It's important to understand what that is, because there are ramifications there, in the extreme situations. You can't just, people say just trust the math, but it's, and first of all, you are trusting that, if you validate the cryptography, right? Like there could be flaws there, but more importantly, there are other things there. So, for example, the math might tell you that this, coming back to finality, that it's Byzantine fault tolerant, and it can tolerate some number of the actors misbehaving, but nothing says you can't have more than those actors misbehaving. And then if you go to dig in deeper as to why you believe that's not going to happen, there's actually an economic argument for that. It's not just like pure math. As Guillaume mentioned with the IBC, there's lots of points where you could potentially compromise the integrity of the messages being sent back and forth. So like if you're talking with a low trust chain, but your contract state depends on the state of the other chain, if those chains, block producers, for example, are compromised and they change their token contract, that fundamentally changes, the state. Like they could just lie and tell you something happened on that chain that didn't happen. So that has to be considered, especially when you start having these intricate, interconnected mesh of dependencies across multiple chains.
Okay. Anything to add to that, Matt?
I think Areg hit it spot on, really. There's always some trust, some root of trust, or some web of trust. Yeah, spot on.
Yeah. I mean, yeah, if you don't trust the blockchain itself, it doesn't matter what's built on top of it if the foundation, you don't trust the foundation. So that's a very good point. So what is IBC in the wider industry?
I can opine on that. So I guess I believe that the term was coined by the Cosmos guys when they released their white paper. I believe that was in 2015 or something. Yeah, around that time. So I believe they came up with the IBC, inter-blockchain communication moniker, which has been reused, I guess, across multiple ecosystems, including Antelope. I remember personally, like the first time I heard about that was, by Dan Larimer. He mentioned it, I think, in some post somewhere, and it's. I mean, some people might disagree. I had discussions on Twitter with some of the Cosmos guys that seem to disagree, but to me, it's a very generic term, I guess, that has been around for quite a while. That is, in my opinion, quite okay to use in the context of what we're doing here. So now there's a lot of things also that people have been, I guess, trying to pass as IBC or other alternative technologies that, I mean, were quite easy to implement, but also quite easy to break. Thinking about these kind of Oracle multi-sig contracts where, like you, in contrast to what we're doing here with this like trustless IBC, where you don't have to trust any additional set of validators or custodians or witnesses or whatever. In a lot of these other systems, that's how the interchain communication was handled. So you would have a group of people that were essentially running the client software of two different blockchains, and then they would observe what was happening on blockchain A, and when they needed to replicate this on blockchain B, they would do like some sort of a multi-sig, and they would like some threshold, like 3 out of 5, 4 out of 7 of these custodians would essentially sign a transaction that would like mimic the action that you wanted. So in the case of a wrap token, you would lock your tokens on chain A, the oracles would witness that, and then they would craft an MSIG saying we're going to mint the equivalent amount token on the other chain, and then that's how the link was made. And now the issue with that is because in order to allow the redemption of these wrap tokens, you also need to sign that MSIG on the way back, and that MSIG releases the funds that have been locked on the source chain. So at some point, if the group of signatories decide that that the pot is big enough and that the collusion now becomes interesting, they have the ability in these systems to run away with the funds. And it doesn't really matter if it's an inside job or if the keys have been compromised or whatever, the results are the same. And that happened several times is an understatement over the last, let's say, like 12 to 18 months, probably before that as well. But especially in the last year and a half, there's been several very high profile cases of like trusted oracle setups that failed in the most spectacular ways, where hundreds of millions of dollars of luck tokens were basically stolen. So it's quite important, I think, to do things right and to go the the long and hard and difficult road of like doing it trustlessly, like cryptographically based. But in the long term, I think it pays off to build on these solid bases.
Yeah.
Cool.
So, yeah, go ahead, Brendan.
Anything to add? That it was pretty thorough.
Yeah, that's pretty great. Yeah, nothing to add here.
Okay, cool. I thought I'd flip these next two questions around. So, could you all explain the IBC token contract in relatively simple terms, like how tokens get literally passed from chain to chain? And
these are different contracts. The way we've built it, there's let's call it like the IBC contract, and then we have the wrap lock and wrap token contracts. So essentially, the IBC contract, its purpose is solely to verify if a block is valid, if it has been like included in the chain in a provable fashion, and if an action contained in that block is also like included, really took place in the block itself. So IBC, the IBC contract really serves that purpose of proving like actions and blocks, so that it can now be used as a building block to more elaborate systems. And the wrap lock and wrap token contracts, this is how they essentially work, where if you lock, again taking the example from before, if you lock some EOS on EOS and with the intent of minting some wrap EOS on Wax, what you're doing is you're sending these tokens, these EOS tokens, to the wrap lock token contract on the wrap lock contract on EOS. That generates a proof that now can be submitted to the IBC smart contract on Wax and can be used as the condition to mint these wrap tokens. So if I'm able to submit a valid proof that I've locked tokens on the EOS side, if I'm able to submit that to the Wax side, the equivalent amount of token is minted. And of course, there's a replay protection mechanism so that you can't prove the same thing twice, for example. And the reverse process applies when you want to redeem the original asset back on EOS. So you take these wrap tokens on Wax, you burn them, you submit the proof that you burn these assets. Like burn is a retire in the Antelope terminology. So you retire these tokens, and then you submit that proof back to the on the EOS side that will now unlock these tokens that were locked previously and send them or make them claimable by you, essentially. And that's just one example, by the way, like of what can be done. As we hinted at earlier, there's many other construct that can be built on top of IBC to have multiple chain governance, to have like a staking resources on a main chain, having like virtual resources allocated on side chains. You can build any sort of proving mechanism. If you had something like Eden, for example, you could recognize the Eden NFTs on other chains and expand their use, their utility to other ecosystems, and so on and so forth. So
the way this is structured, this layered approach, is it builds on this fundamental of just authenticating message passing between chains, which you could use, as Guillaume was mentioning, for different applications beyond token contracts. And right, like so, like the foundation of that is this one we're calling the bridge contract that could be operated as this sort of system contract, if you want, that multiple developers could leverage, do the hard stuff of proving and moving messages around, and then you build on top of that whatever kind of application you want, one of them being this token contract.
All right. So thank you for explaining IBC. Let's move forward to a high level of instant finality. So can we go into a high level overview of the current industry landscape surrounding instant finality? Like, where are we? What are the next steps, and what's like the end goal?
Guillaume, do you want to start us off? I feel like you do a great job.
Yeah.
Give it a overview
Yeah, I
of
guess.
the current state.
Right. I mean, yeah, it's obviously like this is a space that is evolving very, very fast. Like there's new projects coming out all the time. So it's really hard to stay up to date with everything that's happening everywhere. However, when it comes to, let's say, state of the art consensus mechanisms right now, there's been quite a bit of research that's been done. I mean, like, people probably have heard of Ethereum 2.0, Casper. There's also we spoke about Cosmos a little bit earlier. It has the Tendermint consensus model. So these are I guess like previous generation compared to what we're doing. If you look at the time that these algorithms were formulated, I think it was around like 2014, 2015. It takes a while before, of course, some some crazy nerds in some university come up with these things, and eventually, like, it gets tested, and it gets like researched and tried out before it can make its way into a blockchain. So it took, in both of these cases, these algorithms were designed a long time before they actually became used in production. And similarly, the one that we selected on our, as we were approaching this, is an algorithm called Hot Stuff, which comes a bit later in the chronology of consensus algorithm. I think the first paper was published in 2018 or something. I think originally it was by VMware. So VMware came up with the original Hot Stuff algorithm, and then it was selected by Libra, which was the Facebook cryptocurrency project, as the essentially the most, like, the I guess, like, the better suited consensus model at the time. And there's good reasons for that. Like, as Areg and I have been researching this over the last few months, we've discovered the reasons why this is quite interesting compared to what already exists. There's some very good trade-offs that can be made there's a degree of flexibility and a degree of, I guess, like parameterization in that consensus algorithm that is very, very exciting. Like it really opens a lot of possibilities. So in a way, I feel like we are at the cutting edge of this, I guess, research. I'm not aware of anyone else having deployed or even working on hot stuff consensus for a blockchain project now that Libra is no longer no longer being developed. I think it like it changed names. I think it was called DM for a while, but that also got shelved at some point. So as far as I know, there's no one else who's been working with this. But I think it is an opportunity and like a I guess like a potential source for renewal and in interest of now Antelope as we start rolling it out. I think it will have its moment in the in the spotlight.
Yeah, I'll just add that. So there's a whole there's a lot of BFT algorithms out there used by different blockchains. I think ones that are most relevant and interesting to look at is Casper and Tendermint, and then now Hot Stuff, which is what we're basing the algorithm that Antelope will be using for instant finality. And these are all, I mean, ultimately trace them all back to classical BFT algorithms. This stuff is very old, but has been improved on over the years, most recently thanks to blockchain, focusing on liveness and performance and things like that. You also there's cutting edge stuff. I mean, Guillaume and I were talking about advances on top of hot stuff and whether we can squeeze better time out of it. But there's also a concern of getting too latest and greatest and cutting edge, and whether you trust the safety of it. How much validation has been done. So we think we found a good balance there with the hot stuff, and particularly we'll talk about this chained hot stuff variant or the event-driven hot stuff variant. One thing I would point out, without going into too much of the details, is two properties that I think are very interesting compared to what else is out there or was commonly out there. Those two properties are linearity and optimistic responsiveness. So when it comes to linearity, this leads to one of the other deliverables as part of the RFP, which is BLS aggregate signatures. Linearity is this idea of reducing the amount of communication that you need between the various consensus participants to scale linearly with the number of participants rather than what is often done is quadratically scaling it. And it does this using a cryptographic scheme that allows you to take different shards, I guess you could say, of signatures and combine them together to form a signature which represents one signature from this kind of aggregate public key, which is the aggregation of all the different participants' public keys. And that is the magic, basically, of taking this from quadratic scaling to linear scaling, which is important in terms of increasing the number of participants for the sake of decentralization, for example. The other big important change is, or this property that's really desirable, is optimistic responsiveness. So especially if you look at, say, Tendermint and Cosmos, you can kind of view them from the lens of Hot Stuff. Hot Stuff has a three-phase consensus model, whereas those two are two phases. So you can view that as a negative where you're adding an extra phase, more latency. But on the other hand, it does get you this benefit of optimistic responsiveness, where you're not waiting an arbitrary amount of time to listen from enough participants to feel like you have the information you need to move forward. And what this gets you is to basically move as fast as network conditions allow. And in practice, we think that will make a big difference in terms of the practical time to finality.
Yeah.
Cool. You guys are swimming in the deep end now. So
Yeah.
it's going to turn into
You asked for
Areg.
it.
Areg, yeah. I just love the phrase optimistic responsiveness, but I couldn't tell you, like, someone needs to look that up and report back to me so I can. All right, you hinted that we're getting close to fundamental limits, and this is something that came up in our conversation. Areg, do you care to add anything to that?
Yeah, I mean, so part of that optimistic responsiveness is to not have these arbitrary restrictions on time. I mean, even something as Guillaume and I were talking about this just recently about like chain hot stuff versus basic hot stuff, and how do we get the best of both worlds. And one thing with chain hot stuff, if you do it sort of naively, is you're putting each confirmation at at the level of a block, and this reminds me of the current algorithm of EOS, and the reason why it scales with the number of producers, the time to finality scales with the number of producers, is because you're arbitrarily limiting it to one confirmation, like from 1 BP per block. So every half second, 1 BP can provide one confirmation. With linearity, you can have, and chain hot stuff, naively applied chain hot stuff, you can have all BPs provide their confirmation in what's called a quorum certificate per block. But even that's maybe not fast enough because you need 3 phases of this stuff. So instead of waiting 3 blocks, it'd be nice if you could just go as fast as network conditions allow and maybe get 3 blocks within less than half a second. Of course, to actually do that, I mean, you could do that if you have a network that's closer together, like a local network, or maybe a broader network that has fast links between each other. But when we're talking about a global decentralized network, with nodes all over the world and lots of hops and processing along the way, it starts becoming very difficult to have a sub-second time to finality just because of the time it takes to send the messages from one computer to the other, validate and send, and just fundamental computation and network speed times may become the bottleneck at some point.
That's pretty exciting. I like to think we're pushing those limits. So I don't know the appropriate segue into this exactly, but during our conversation prior, you touched on the mathematical proofs that you guys have been working with, and you kind of went into the difference between mathematical proofs and concrete cryptographic proofs. How does that relate to what you guys are working on? And
okay, I'll give it a shot. So there are, as part of what we want to achieve with this new finality algorithm, as part of what's required in the RFP requirements, was to ensure that we can provide cheap proofs for finality. So that, as it relates to now, actually IBC, so there's a connection there. IBC as it exists now, and it works with the existing algorithm, the existing finality algorithm that Antelope has. But it's dependent on the consensus algorithm used. So when we change the consensus algorithm to use instant finality, the IBC contracts will have to be updated to use that. And so we wanted to make sure we preserve, we talked about the design, so that it was meant for IBC. We want to make sure that we preserve those designs that allow for better IBC, and then actually go better, do better at it, actually make it even cheaper to validate. So now you have one signature to validate rather than many to prove a block is final on a different chain. So those are the kinds of things we talk about when we talk about cryptographic proofs. A cryptographic proof of finality of a block that a smart contract can validate. Another cryptographic proof related to that is what happens. So we talked about Byzantine fault tolerance and how there's a certain number of Byzantine faults you could tolerate before where nothing goes wrong. But what if it goes beyond that point, which it theoretically could? And the only reason it shouldn't is because you've designed economic incentives to make that unlikely to happen, or make it financially disadvantageous to do so. But in order to actually ensure that, you need a mechanism to enforce against bad behavior. And part of that mechanism would be cryptographic proof. So let's say someone, worst case scenario, they've been defrauded, they've a set of like 2/3 or more of block producers, for example, worst case scenario we're imagining here, have colluded together to create a fake chain that they're tricking with the double spend attack. They're tricking their victims on to try to make some money off of that. How can we guarantee through the properties of this chain that that victim has enough, let's say they're a light client, validating the proofs so that they believe that this chain is final so they can rely on the side effects of that? How can that client get sufficient data from that process such that later, if they discover that was not the canonical chain, the real chain is somewhere over here, I don't have my tokens on that version of the chain, how could then they take this data and the data in the public chain and use it to construct a proof, a cryptographic proof to show these set of actors were double confirming blocks in an illegitimate way, and so we can actually blame them for that. They're held accountable. So that's another side of cryptographic proofs that we're thinking about ahead of time and actually requiring as part of the deliverables to design for that and provide reference code to show how that could all work in smart contracts to validate it. On the mathematical proof side is sort of like, okay, but how do we know these properties hold, like rigorously? With mathematical rigor, how do we show it's safe? How do we show this protocol has good liveness properties? And we have that accountability thing we talked about. It's all about just feeling very confident that this algorithm does what we say it does. I don't know if Guillaume, do you want to add anything to that?
No, I think that's very very thorough. I mean, you could look at the mathematical proofs as the, I guess, like foundational work at the design level, where we want to make sure that certain properties, Areg named them safety, liveness, accountability, are demonstrable at any point. You can verify that these property holds if initial assumptions are followed, and then from there, when you complete the system, when it's completely implemented, this is essentially applied through. This is measured and verified through applied cryptography. So these proofs are essentially like the cryptographic schemes that we use are essentially, they conform to these proofs, and they allow to demonstrate that these properties are upheld and maintained at any point.
Areg, Guillaume, anything that you'd like to add as far as some like key differentiating features, stuff you've been working on? One thing that occurs to me is like the security considerations that you were kind of touching on with the cryptographic proofs. I mean, so I just wonder how much time you spend thinking about how to attack what you're building versus just building what you want. You know, it's like, how often do you think of some solution and you're like, this is brilliant, and then you're like, oh, but you know.
So it's definitely an iterative process.
Yeah, exactly. I was gonna say. I mean, as you build these things, of course, you have. I mean, like there's always things that, like edge cases and like contextual situations that need to be handled correctly, and there's a fair share of these things happening in Antelope, for example. The different at different versions, different points in time, some of these proofs are calculated differently. Like basically, if you've activated certain chain features, now it changes some of the underlying mechanisms. Some edge cases also that don't necessarily happen very often, but could happen, such as, for example, let's say in current Antelope setups, if you had 1/3 plus of the block producers that were offline for extended periods of time, that creates a scenario where no progress, like no finality progress, can be achieved until that situation is resolved. But an IBC system would still have to be able to recover from a situation like that. So originally, the first iteration that we had didn't take that into account as an edge case, and Areg pointed it out. What happens if, and we're like, oh yeah, so we need to change that to take that into account. And there's definitely some. It's an iterative process that requires also, I guess, like constant vigilance as upgrades are performed and as things change here and there, because we want to make sure that we always respect the consensus algorithms of multiple chains as they are as they evolve over time. So it's definitely there's definitely a lot of, I guess, factors to take into consideration. And it's the good thing is, well, I mean, so far we've been through multiple audits from multiple auditors, and everything is great. But yeah, like it's a constant process as you're building these things. You have to always think, okay, what happens if the proofs are constructed in this way? Is that gonna go true, or is that gonna be stopped by the checks that we have in place? And if you remember, like not so long ago, there was a hack on Binance Smart Chain. They were using an older version of some of the Cosmos software stack, and I think as the hack was described by researchers, the Cosmos developers realized that their newer version was still potentially like exposed to that problem, and essentially it was just they had just forgotten to handle a specific case where you could just specify like wrong values that would trigger a specific branch in the verification that would like simply not verify the proof. So I mean, we have to be very, very vigilant as we work on these things. And there's definitely going to be a as we open source the code, we will invite as many developers to take a look at how we're doing things and getting familiar with it and try to break it. If there's an issue with it, better know better know sooner than later, you know.
So going back to something earlier, what's the timeline for third-party developers to build on this? Like, what do you see them? What are they going to start developing? And as you know, the first applications aren't always the most complex, but what are they going to build towards, and what kind of applications will all of you be excited to see?
Well, I mean, some people already started. We've been as we're progressing to the IBC milestones, as code is reviewed and code is released. Some of the, I guess, like satellites and various infrastructure that's related to IBC is already public, and there's already some teams that started looking into this and reaching out and asking to some guidance to start building on top of that. So it's not everything is out yet, of course, as we said, like it has not been deployed to mainnet just yet, but we're hoping that it won't take very much longer. Initial multi-signature proposals have been issued to all the networks of the Antelope coalition. Now it's up to the BPs to proceed and to essentially create these IBC accounts that we will then configure. And once they've been initialized properly, they will be turned back over to the block producers of the networks, and then block producers will activate it when everyone agrees and everyone is ready. So essentially, at that moment, we also will release the source code, and then the entire solution can now be like anyone can start looking into this and build on top of it. There's already, like I said, some people that are already building various things. I'm not gonna not gonna say who, because they didn't grant me that. It was told in confidence, but it's doable now, and I think it will only accelerate as we releases the documentation, as we release the entirety of the code, and as people start spreading the words. I think just like a lot of the other things in this ecosystem. I mean, there's a first a phase of like discovery for everyone to, okay, now this is available, how does that work, like how can I integrate that in my application? But we know a lot of people are definitely very excited. A lot of dApps have reached out over the last few months, and they definitely have big plans to build on top of it. So we're expecting this to start like slowly, but start ramping up quite soon. This is where the last sprint. So
Guillaume, you mentioned something that I think is worth pointing out here. So we're talking about how right now, so it's already on testnet, but for mainnet, currently it's in the process of waiting on BPs to approve multi-sigs. But that's actually just for really a nice name and kind of having blessed contracts.
Yeah.
The reality is that this is, maybe you could talk about that a little bit, about like different layers. We kind of mentioned it earlier, but also the fact that you don't really need permission to build on it once
it's a good point.
it's there.
It's a very good point. So essentially, one of the there's as these contracts are developed or deployed, of course, there's this the bridge contract itself that serves to prove the actions, as we were saying earlier, and then there's the wrap token contracts that are used to represent tokens that are locked on a certain chain and made available to a different chain. So when most of the use cases that go around these wrap lock tokens have to do with liquidity. So there's an incentive if you want to for people to use the same contracts, to use the same representation of these wrap tokens, so that you don't end up with several representations of the same thing that could be like different. Like maybe like there's one contract here, one contract there, and so on and so forth that all represent like a wrapped EOS or a wrapped USDT, but they're not the same. So it makes it complicated for applications on the other chain to support multiple competing quote quote proposals. So in order to address that, as we discussed with the coalition, we said we will have these quote quote official contracts that we will that the chains will promote, that will be essentially under the control of the network, of the block producers, that will be like the ones that are quote quote supported and that people are invited to focus their attention on. But it is not a requirement for this technology to work. Anyone can essentially take the code, just like right now people don't create tokens on the official EOS.io.token account. They do take a copy of the EOS.io.token code, they copy it to their own account, and then they issue their tokens there. So it's the same mechanism, if you want, it's the same logic, but it does not reside in the same space. So we're giving the same flexibility basically through that the release of that software, where anyone can take, for example, the wrap token and wrap lock contracts and deploy them on any network and make their own tokens available for interchain transfers. And it's important that to highlight that, because our goal is not to close the system and making sure that only like the official versions are supported. We're doing that to help concentrate liquidity, but it's by no means a requirement to use the official versions. As a matter of fact, there's potential arguments to be made in favor of using other versions if, for example, someone was to build a liquidity aggregation mechanism that would leverage the Yield Plus program, for example, or things along those lines. So in that case, this is not going to be done in the official versions, but someone could create a product that would essentially like offer this additional yield to depositors or to stakers using their own version of these token contracts. So if that makes sense.
Yeah, that's not something I thought we were maybe going to get into, but I'm curious if you could say a little bit more about what you see as the potential for IBC with the Yield Plus contracts.
Well, I mean, the general idea behind Yield Plus is to essentially incentivize, I guess dApps and on-chain liquidity, like liquidity
TVL.
and
Yeah.
TVL, as we call it, like total value locked. It removes tokens from the exchanges. It removes tokens from the quote quote float of the market. So these tokens typically are staked for longer periods. So we've done quite a bit of research that has been published in the Yield Plus blue paper and in the monthly reports for the Yield Plus program that highlight these the relationship between market cap and TVL between chains. Like if TVL goes up to a certain point, it does also bring market cap up as well. There's like diminishing return at a certain level, but there's definitely a sweet spot that the Yield Plus program is trying to identify essentially. So here with the context of IBC, one of the interesting question becomes if we are able to essentially attract other, let's call them like not necessarily stable coins, but let's call them like high liquidity tokens, and we're able to lock them on Antelope chains, we are contributing to that TVL, and we're contributing to the market cap essentially, like to reducing the float and to increasing the utility of the token, basically. So this is one of the aspects where IBC intersects with Yield Plus. As it stands, the only external token that is supported is USDT. However, there's plans at some point to support, well, Ethereum and like Ether and any other wrap token coming from other ecosystems that have achieved a certain liquidity on the market or certain stability in price. So this is how the two are kind of related.
Cool.
So going back to Trustless, can users provide their own sort of proof? How does that work? How would a user go about doing something like that?
Yeah, it's a very good question. So essentially, like the smart contracts on a given chain will verify the proof. So essentially, like that proof that is submitted to that smart contract will be verified. So it doesn't really matter in terms of like safety and security where that proof comes from, how it's been generated. We just have the smart contract that will essentially verify a number of things with that proof, and at the end will reject the proof if it's invalid. So that's not a requirement for safety. However, when it comes to let's say permissionlessness and censorship resistance, it is quite important for this infrastructure to not rely on any I guess authority or whitelisted relayer or additional trusted environment that essentially like is a requirement for the whole workflow to go through. So there's before these kind of IBCs, which are I think the current, I guess, like at the cutting edge, let's put it this way. There were a number of iterations that were essentially like the step before. If you want one good example in the Antelope or back in the day ESIO space was Buscore. So Buscore was that chain that launched in late 2018, and they had actually a cryptographically secure, as far as I can tell, IBC wrap token mechanism. However, it did require a whitelisted relayer that would essentially like synchronize the two chains, that would transmit continuously block headers from both of the chains and would update the internal state of both of these chains so that these wrap token transactions, interchain transactions would go through. And the problem with that approach is that although there's no issue of safety or security, there is the issue of potential interruption of service or selective denial of service or censorship and other similar type of I guess like a denial of service, if you want, for you, a user. So when we designed our IBC, one of the I guess criteria that was a requirement was to not have this requirement of a third party acting as a permissioned relayer, and also we wanted to make sure that the user themselves would be able to like generate their own proof and submit the proofs to the other chain. So that was essentially to ensure that permissionlessness and that censorship resistance would be maintained. So we got pretty far in that direction. It's not as perfect as I would like it to be. For that, unfortunately, I think will require instant finality and a bit more work when it comes to making these proofs available. These are the discussions we're having these days as we're zeroing in as we zero in on the last details of the proposed implementation for instant finality. But the idea is really to make sure that there's as little supporting infrastructure that is required, and that a very light client, such as a web browser, for example, would be able to verify these or generate these proofs and verify the context of these chains and ensure a very like highly available system that pretty much anyone can benefit, like can use in their workflows without the dependency for third party, like I guess like central point of failures, even though they might not be putting the money at risk. We don't want them to be able to selectively deny service or for users to depend on them as they perform these transactions. So we have to start somewhere. So we started with the diffuse history solution that we use to generate proofs to a proof server. This is not a requirement in a sense that we've built also more complicated light clients that will fetch these proofs by themselves and are basically could be we've done it in the browser. It's not necessarily a big deal. It's just that it's a bit less convenient because now the client has to know more about what data has to be fetched and has to calculate more things. So we decided to create this intermediate step, which is essentially what we call the proof server. So there's a server that the client can query and can have generate these proof in ready to use shape. So that's one of the things that we have right now. We want to reduce the reliance on these proof servers as much as possible with instant finality to a point where any normal node would store all the information that's required for these proofs to be created, and then at that point we would have, I think, a very complete and very lightweight solution that can be really powerful in all use, like all contexts.
I think, Adrian, before the IF changes, though, like as you mentioned, it is possible for you to just grab the block headers and construct the proof yourself, the what we call the heavy proof, the proof that's based on the finality algorithm. We've also talked about, instead of relying on this extra software, maybe as part of the standard APIs provided by Node.js, we can have the Merkle witnesses, the hashes, so that you can construct through standard APIs the what's called the light proof. That actually goes back to the question, the discussion we had earlier about like there's no permission, you don't need to coordinate with some central party. No matter what everyone else is doing, So the contract is designed, the bridge contract is designed so that if other people are adding in their own heavy proof, so things are advancing, you could still go back and provide your own heavy proof, but you can also leverage the latest heavy proof to go back and prove things a long time ago using the structure that Antelope has designed for IBC, but it allows you to basically go in and prove the whatever actions you care about in the past using logarithmically scaling Merkle branch proofs, essentially. So I think like everything in there is designed to allow a user to be able to construct using readily available information, construct their proofs, send it over to the other chain, and get it validated independent of what anyone else is doing.
Yeah.
Which I think is really cool, like property of this IBC.
Yeah. So essentially, like we, as part of this IBC, we support two broad proof schemes. We call them heavy proof and light proof. Now, the heavy proof is essentially the verification of finality according to the consensus model. So under Antelope, for a block to become final, it needs to be extended by essentially 2/3 plus one block, block producers, times 2 rounds. So like you have to essentially go through 2 rounds of 2/3 plus one block producers, adding a block on top of a like reference block for that reference block to become final, irreversible. So now the heavy proof essentially replicates that. So we verify for a specific block that we've that we've achieved essentially consensus by verifying all of these signatures that are required to reach finality for that particular block. Now, once that's done, we essentially save the Merkle root of that block that we just verified in the contract's RAM, and in such a way now that any block prior to that one can now be also proven through what we call the light proof scheme. So that's one of the properties of a Merkle tree, is essentially as the Merkle tree grows, as you're adding more leaves to that tree, it essentially, in the case of Antelope, there is a kind of data structure that contains a representation of, like a minified representation, if you want, of that tree that evolves every time you add one leaf, from which you can reconstruct essentially like cryptographic chain linking any block to the current root. So if I have like a block 1000, for example, that I've been able to prove, now I want to prove an older block, let's say block 500, I can take that Merkle tree structure and construct a proof that will connect my block 500 all the way back to the root of the block 1000, and that cryptographic proof now can be used to demonstrate that the specific block has been included in the history of the chain. So by doing so, it's a much lighter version of the heavier proof, hence the name light proof, that can be verified faster, that takes far less space, and that allows to prove any action or any transaction that occurred since the genesis of the blockchain. Now, there's a downside to that, which is essentially, in order to generate that proof, you need to also have access to more historical data and specific like data points in time to reconstruct that. So that's a downside, but we're also working on making this data structure as lightweight as possible and as portable as possible for convenience. I don't know if you wanted to add something.
Well, just there's that downside, although it can be mitigated, as you mentioned, by being very efficient about how we store it, especially for the most recent blocks, which are most likely going to prove. The other thing is, like, why not just go for the lighter one all the time? You still rely on the heavy proof to advance things, right? So like heavy proof is necessary always to get the latest block confirm or have the chain believe that the latest block with its block Merkle root is true based on the consensus algorithm. Once you have that, you can then leverage the light proof. And so that's advantageous because you imagine you have like hundreds of different applications all trying to communicate back and forth. You don't have to, you can, if you want to, it might make sense to do so, but you don't have to use a heavy proof for every single action. All you really need is a heavy proof for every block from the source chain onto the destination chain. Just one, like you could have a service do this, but again, it's not required to have a centralized service to do it. Anyone could do it. But for efficiency, if someone's doing it for you, you could just leverage that and just use light proofs to actually efficiently prove your actions.
Yeah.
So now going back, let's tie everything together. So IBC benefits from instant finality, but instant finality does not necessarily benefit as much from IBC. Is that true? And do you mind going into the relationship between both?
Do you want to take this or should I?
Yeah, no, I can take that. I'll start, and I'm sure you'll add a few things. But so essentially, IBC, as we discussed earlier, like we currently have to follow the current consensus mechanism of Antelope, which takes just under 3 minutes to reach finality in most cases. So because of that, of course, there's a significant delay before an IBC transaction can be considered final and safe. And this is one of the definitely very interesting benefits of instant finality is now we'll be able to reduce that time to like a few seconds, like low single digit seconds, which drastically improve the user experience and can also extend quite a bit the range of applications that can now take advantage of that. So that's probably one of the, I guess it's one of the main reasons why I'm interested in instant finality, although it's not the only one. Like there's quite a few others, but this one here I think brings an undeniable benefit when it comes to fast like inter-blockchain proofs.
So real quick before you jump in, Areg, so instant finality essentially kind of like supercharges IBC, more or less, what I'm hearing.
Yeah.
Now, is instant finality on a single chain is it comparable? Let me say it another way. Is instant finality on IBC as fast as instant finality on a single instance of a public blockchain? Is there much difference there?
Maybe comment on this.
Well, I mean, like there's
Yeah.
there's a tiny bit more latency, of course, because like that information, that proof has to be relayed to another chain, has to be verified by that smart contract, but it's not very much in the grand scheme of things. Like if we are right now, for example, like if it takes just under 3 minutes to reach finality on a specific block as it stands, we can have, like the proof verified by the smart contract, like in the next 0.5 seconds. Chances are like 0.5 seconds after that's done. So the same kind of would apply there. So like you would have of course a bit of latency that would represent the time that it takes to build the proof, to package it, to submit it to the smart contract, and for the smart contract to verify it. But and like for all intents and purposes, it's pretty much the same speed, basically.
Yeah, so it's just to add to that, that's the little bit of extra time added onto, like, so you first have to wait until it's final before you can prove to the other chain. And then there's a little bit of extra time, as Guillaume mentioned, to generate the proofs, validate it, and all that. But that's for one hop. And I just to stress the importance of like how big of a difference instant finality can make to IBC. It's not just what necessary. I mean, some applications as simple as just one hop, just sending a message from here to there. But when you get more complicated, there might be a lot of back and forth messages needed to carry out some overall cross-chain operation. And imagine with the current algorithm, 3 minutes, each message taking 3 minutes back and forth. I mean, I would use an analogy of like going from snail mail to email, just the back and forth, right? That makes a huge difference if you drop like the latency from each one from 3 minutes to just like a couple seconds. There's more I think that can be done there, and this is far more speculative about like the future of IBC as I see it. Like I said, this is the basic mechanism of message passing. There's potentially other things one could do with other protocol changes that could leverage, could kind of compress multiple back and forths needed to enable a cross-chain sharded application and sort of speed up the time it takes to do a single operation. Ultimately, they're all based on this mechanism of sending messages back and forth, but and so they benefit from instant finality. But there's a lot more to it, I think, that we could explore with IBC in the future. But as it is just right now with message passing, I think IF is a huge benefit just because of like how big of a difference that makes.
Yeah, it's a very good point. Like when you think, let's say, how communication used to work when people would send letters through the mail, like through courier. Like I'd write a letter, you'd get it like maybe 2-3 days later, you'd respond, I'd get it 2-3 days later, and so on and so forth. So of course, if you're able to shrink that delay, that communication delay, to a few seconds, then you can have that back and forth happen in pretty much in real time, and a whole new range of applications now become possible that were not possible before that. So especially when we start talking about, let's say, like sharding, or what I like to call side chains, and like very very rapid synchronization of state across different chains, that makes a huge difference, because now that synchronization can happen like near real time, and it's not artificially delayed by these like multi hops, like jumps basically.
Awesome. And yeah, that's some of the stuff that we could get into in a further conversation, which I think we should have, which may touch on some of the implications of the adoption of the hot stuff consensus and other improvements from instant finality, including sharding and sidechain type stuff. And Areg could probably summarize or tease some of those better than I.
Yeah, so I mean, I mentioned some in IBC, like this is the basic fundamental mechanism, but how could one build upon it to address the problem of scale, really, scaling applications? There's all these governance aspects to think about, like what do you do with accounts? How do you manage accounts? How do you manage resources? There are a lot of things to figure out. Like we're starting with this primitive mechanism of message passing, and then with instant finality, improving on it and making it faster. But there's a lot more to do beyond that. So I think there's a lot of a lot of interesting discussions to have there. A lot of things we have to first figure out, frankly, regarding IBC as it goes in the future. Regarding instant finality, there's a lot we've already discussed, some of which is like speculative, that I think would be interesting to talk about. So one of the things we didn't mention here that Guillaume and I have been talking about a lot is how with instant finality, we've really been thinking about how some of these roles are distinct. So we've often thought about block producers, but really at the level of the consensus algorithm, we're starting to think about, well, there's really a block proposer, and there's a block finalizer, and there's a consensus leader, and those are technically all different roles. For instant finality, what we're doing initially is just collapsing it all into one role, block producers. Nothing changes there. But it's really interesting to think about what could happen if we were to actually decouple some of these roles. What opportunities do those enable? And not only that, I referenced the proofs, the cryptographic proofs, including the one of, I guess what it called a finality violation, where the victim was tricked under a double spend attack. How did they prove that they were tricked so they could penalize the bad actors? So I referenced that a little bit in terms of the actual algorithm supporting that. So, that's a nice property to have in the consensus algorithm. But there's a whole other layer of a consensus mechanism that builds on top of the algorithm, which adds all the economics to it, right? Which I said was very important. It's one thing to have these like CS properties of, Byzantine fault tolerance and everything, but it's a whole other thing to trust that your mechanism is something you can actually rely on. And that's where the economics comes in. And so that's where we could maybe talk about things like what future does this enable for augmenting the security of our proof of stake consensus mechanism with things like bonded state that can be slashed. So what are the economic benefits? What are the security benefits of that? So yeah, I think there's a lot of interesting things to talk about, both in IBC and IF, that obviously we won't have time to in this session.
Yeah, and then we haven't even touched on the governance implications of just IBC itself, like interchain governance implications, which I know y'all have been discussing a little bit. So that's something to maybe like touch on in a further conversation. And then before I let you go, I've heard 6 seconds as kind of like, I think it's the conservative number that y'all have been throwing out there. But if you had to wager, what would you think the average? Because I know it's not like as simple. Like it's not always going to be like a real simple transaction. It could be like a multi-step transaction. What would you wager that instant finality ends up being like around average time?
Yeah, I guess it's there's quite a few factors that will play a role in that number, and that will include, for example, the logical and geographic distribution of the nodes that are essentially composing the network. How many layers do you have between, like, of essentially like nodes, hops between, say, block producers, and how well they're meshed together? What are the overall conditions on the network? So of course, the more global, the more decentralized, the more participants in the system, you can think it will take a bit more time than if you have like all of your nodes running on the same computer or same data center, and that are very, very tightly connected. But I did run some, I guess, let's call it like preliminary tests that are, I think, relatively accurate. And it was 6 second would be a conservative number. It was more to the tune of 2.5, and I think we can potentially do even better. So we could have possibly a little bit lower than that. It depends on a lot of things. So I mean, of course, like performance will vary across different networks, across different network, like topographies and meshing characteristics. Also with the load, like with the how big are the blocks, and how much of the I guess like the bandwidth is being consumed. But that's the general ballpark that I'm estimating.
What are we looking at timeline for instant finality currently? I'm not really remembering where that's.
So I believe we're planning to have this go live on Jungle, or we said Jungle, but it might be a new public testnet that we set up specifically for that. We're aiming something like, I guess like May or June for that milestone.
All right, sweet. It's gonna be a fun summer.
Yeah,
a fast summer.
yeah, exactly.
Anything you guys want to add before we wrap it up? All right, Jonaed, thanks for being here and having this really in-depth conversation, and for tolerating our lack of ability to ask like really knowledgeable questions. But yeah, Jonaed, take us on home.
I'm gonna listen to this like 3 or 4 times to be able to like comprehend it. But it's good to be surrounded by really technical people who are firsthand working on these projects and to see the space evolve in front of our eyes. So thank you, all of you, for doing that. We'll keep it updated. Is there any way to follow any of your work? Twitter, any other place, blogs, newsletters? Do any of you want to share any of that?
I don't think we've been very very good at that. I think at some point we might start recording these calls that we've been having, especially as I guess like we really like we're kind of entering that phase, I guess, where we've taken most of the decisions that need to be taken. There's still a few things here and there, but now it's going to be a lot easier to start sharing that work and the information now that we've agreed essentially to the game plan. So I think we can probably start thinking about how we're gonna start disseminating that new information. It definitely has to get out at some point. People have to be aware of what's cooking. But yeah, I think it's a good call to action on our end to start thinking about that as well.
Yeah, I mean, if the calls are recorded, I don't mind watching them and tweeting something out of it, just because I know you guys are doing actual work, so I got to pretend to do something, so I'll tweet out some things.
Yeah, I think we can look forward to some sort of website documentation portal of some kind for IBC, Antelope IBC.
Yeah, IBC. There's definitely an ENF initiative right now. I think you're part of that group. Maybe not, but are you like the one that Zach created for the? Yeah, I think you're in there.
Yeah, we just started. Yep.
Yeah. So like we're in the process of kind of organizing documentation together. We'll work with you guys to craft the message, and I think that those guys also wanted to help out. So it will be a process, but it will eventually get done.
Sweet. And if we could get some sort of simple game like tic-tac-toe or something, and just as like a MVP to play inter blockchain tic-tac-toe or
interchain tic-tac-toe.
Yeah, something like that would be really great. I'd appreciate that.
That'd be a fun one.
Yeah. All right, guys, it's been a pleasure. Join us again next time when we get even deeper into the governance side of things and whatever else we haven't touched on today. We'll see what we can cook up. Thanks again, guys.